Thank you very much for having me. I'm really happy to be here. I'm going to talk about formalizing Dedekind reals and decomposability in constructive reverse mathematics, which is a joint project, ongoing joint project with Professor Takako at Tohoku University in Japan. And I'm Mohammad Tahmasbizadeh from Sharif University of Technology in Iran. Okay. We'll start with Bishop's constructive mathematics. We know that Bishop's constructive mathematics is an informal setting for constructive reasoning in mathematics. But there are several approaches to formalizing Bishop's constructive mathematics with base theories suitable for constructive reverse mathematics, which we focus on this subject, constructive reverse mathematics. Prominent examples include the systems DL, elementary analysis, introduced by Troelstra, BIM, basic intuitionistic mathematics, introduced by Weltman, and M as the base system for FIM, foundations of intuitionistic mathematics, introduced by Klein and Wesley. All of these systems are second-order function-based systems. The natural numbers are their first-order objects, and the functions from natural numbers to natural numbers are their second-order objects. What happens to real numbers in these function-based systems? We know that every Cauchy real is a function from natural numbers to rational numbers. And it also can be seen as a function from natural numbers to natural numbers, because we can encode rational numbers with natural numbers. And therefore, every Cauchy real is a second-order object in function-based systems. Consequently, function-based systems are very well suited for constructive analysis based on Cauchy reals. But what about Dedekind real? Because we know that constructively, without assuming the axiom of countable choice, we cannot prove that Dedekind reals and Cauchy reals are isomorphic. So a natural question is, what about constructive analysis based on Dedekind reals instead of Cauchy reals? Okay, we know that every Dedekind real is a subset of the set of rational numbers. And it also can be seen as a subset of the set of natural numbers, because we can encode rational numbers with natural numbers. But subsets of natural numbers are not primitive objects in function-based systems. So this is the problem here. Now we need to solve this problem somehow. One approach is to represent a function, represent a subset of n with its characteristic function. Under this interpretation, every Dedekind real x would be represented by a function f from the set of natural numbers to the set of 0 and 1. But this interpretation enforces the decidability of membership in x, which is not good for constructive interpretation, because we don't want our Dedekind reals to be decidable. Because in constructive mathematics, this is not the case that all Dedekind reals are decidable sets. So this approach fails. But there is another solution for this problem. We can consider set-based systems instead of function-based systems. For example, we can consider CZF, constructive Zermelo-Fraenkel set theory. But the problem with CZF is that CZF is comparatively strong and is not very well suited for constructive reverse mathematics. We are going to find a weak base theory to compare theorems and axioms in constructive mathematics. Therefore, we need rather weak theory. And CZF is very strong to be a weak formal base theory for constructive reverse mathematics. But fortunately, there is another set-based system which is called second order Hating arithmetic, HAS, introduced by Troelstra. And
could you
sorry.
open the chat? Then the bar on the top will be high. Could you open? Yes, that one.
This one?
Could you open it? Once you open it, then yes, then you can close it.
Okay.
Then the bar is high.
Okay. Thank you. Okay, HAS, second order Hating arithmetic, is a second order extension of Hating arithmetic, HA. You just need to add second order variables, capital X, capital Y, capital Z, and the membership symbol, and the full comprehension. The full comprehension says that if you have a formula in the language, then you have a set which is defined by that formula. In other words, every formula defines a set. The only restriction on that formula A is that A must not contain X as a free variable. This is just only technical restriction. Therefore, full comprehension says that for any formula A in the language of HAS, there exists a set X such that for all natural number n is in X if and only if A of n holds. As you can see, HAS is an impredicative system because it allows you to have impredicative definitions. But impredicativity is not a very good property for a constructive theory because this impredicativity notion rejected in constructivism in mathematics. And there are some technical and philosophical reasons for that. But fortunately, HAS has a predicative subsystem, which is called HAS0 by Troelstra. For getting HAS0, you just need to replace full comprehension with arithmetical comprehension. And arithmetical comprehension says that every arithmetical formula defines a set. And an arithmetical formula is a formula that you can't see any set quantifier in that formula, just numerical quantifier. Obviously, HAS0 is a predicative system.
So you mean X is not quantified in A? I mean, you say not containing X
Yes.
as a free variable.
Yes,
Also
A can have parameters, free variable, but can't have set quantifiers.
Yeah, so it has second order quantifiers on cap X. That's forbidden.
Yes, second order
But
quantifiers.
you say
forbidden.
as a free variable,
Yes.
not also as a bound variable.
This particular X which is used for defining the existence.
Okay? And HAS0 is a good constructive theory because Troelstra showed that HAS0 is conservative over HA. That is, for every formula A in the language of HA, not in the language of HAS, in the language of HA. If HAS0 proves A, then HA also proves A. And this is a very good property for a constructive theory, to be conservative over Hating arithmetic. And HAS0 is one of them. We introduced a weaker subsystem of HAS0, which we denoted by HAS00 or HAS00. To get HAS00, you just need to replace the arithmetical comprehension with sigma 01 comprehension. And sigma 01 comprehension says that every sigma 01 formula defines a set. Not every arithmetical formula defines a set, just every sigma 01 formula defines a set, which is a restriction of arithmetical comprehension. And we could show that HAS00 is a good constructive base theory because it is strong enough to develop the basic theory of Dedekind real numbers, while remaining weak enough to serve as a base theory for constructive reverse mathematics. As usual, we could define the left Dedekind cuts in HAS00. We define L is a subset of Q to be a left Dedekind cut of rational numbers if it satisfies these four conditions: inhabitedness, downward closeness, openness, and locatedness. Simultaneously, we could define, as usual, the notion of multivalued Cauchy sequences of rational numbers in HAS00. Let S be a subset of n times Q. We say that S is a multivalued Cauchy sequences of rational numbers whenever these two conditions hold. First is totality and second is Cauchiness. Totality says that for every natural number n, there exists a rational number R such that the pair n and R is in S. And that R is not necessarily unique. You can assign more than one R to one n. You can also assign infinitely many R's to one n. This is the difference between multivalued sequence of rational numbers and ordinary sequence of rational numbers. And it also needs to satisfy Cauchiness. It means that the elements must get closer and closer together. In other words, for every pairs n and r and m and t in S, the distance of r and t must be less than 1 over n plus 1 over m, which is the regularity property in the spirit of Bishop's constructive mathematics.
So I have a question. Don't you assume the uniqueness of R
No,
for each n in the definition?
no. This is the whole point here. Yes. We could develop the theory of left Dedekind cuts in HAS00 and also the theory of multivalued Cauchy sequences in HAS00, and we could show that HAS00 proves the isomorphism between left Dedekind cuts and multivalued Cauchy sequences. And within HAS00, using this isomorphism, we could show simultaneously that both the structures of left Dedekind cuts and multivalued Cauchy sequences are Archimedean complete ordered fields. And in this system, in HAS00, we define R to be the class of all multivalued Cauchy sequences of rational numbers. Therefore, in this setting, every real number is a multivalued Cauchy sequence of rational numbers. And we could also go further and formalize the theory of complete separable metric spaces and also the theory of continuous functions in HAS00. Therefore, we have developed a suitable formal system for constructive analysis or constructive reverse mathematics based on Dedekind real instead of Cauchy real. To demonstrate that our formalization actually works, at least in some cases, we have proved some reverse mathematical results, which we collectively refer to as the problem of decomposability of the continuum. Okay, we need to define the notion of decomposability. We say that a set X is decomposable and denoted by decom of X if there exist two inhabited disjoint subsets of X, namely A and B, such that X is A union B. There are some concrete examples. For example, HAS00 proves that the set of natural numbers n is decomposable because we can decompose n with these two subsets, the singleton zero and the set of all non-zero natural numbers. Because we know that every natural number x is either 0 or not. In other words, the equality in natural numbers is decidable. Therefore, we can decompose n into these two subsets. And we could also show that HAS double 0 proves the decomposability of the set of z, the set z, the set of integers, and the decomposability of q, the set of rational numbers. But the question is, a natural question that arises is that, what about the decomposability of R? To solve this problem, we introduce another sort of comprehension axiom schema, which we call it decidable comprehension. And by decidable comprehension, we mean that every decidable formula A, every arithmetical decidable formula A defines a set. And please note that HAS double 0 plus decidable comprehension is still a subsystem of HAS 0. And here are some reverse mathematical results. With these notions, we could show that over HAS double 0 plus decidable comprehension, the decomposability of R is equivalent to analytic version of WLPO. And analytic version of WLPO is the decidability of equality in real numbers. And the decomposability of R minus 0 is equivalent to analytic version of disjunctive version of Markov's principle, which says that every non-zero real number x is either less than or equal to 0 or greater than or equal to 0. And we could also show that over HAS double 0 plus decidable comprehension, the decomposability of R minus Q is equivalent to this statement that says that for every non-rational real number x, either x is less than or equal to 0 or x is greater than or equal to 0. Okay, that's it. Thank you very much for your lesson.
Any questions or comments?
Really nice talk, thanks. I have one quick question because I maybe misunderstood. For decomposability, you require the sets to be non-empty, I guess?
Yes.
Okay, because otherwise it's a trivial
Inhabited,
note.
actually.
Okay, inhabited
Yes.
even. Okay, good, then I didn't miss that. And then now for this version where you have decidable comprehension, is that strictly stronger than sigma 1 comprehension? Because I was wondering if you can show a formula decidable, doesn't it mean you can actually encode it as a sigma 1 statement?
We didn't investigate the relationship between sigma 01 comprehension and decidable comprehension completely, but I think so. I think it's correct.
I
Because-
guess it's incomparable.
Ah,
But-
They are incomparable.
But I think there are
Okay.
some. Obviously, sigma 01 comprehension doesn't imply decidable comprehension. But I
then
think
I have a
that
mismatch in my
the
head.
the other direction doesn't hold in all cases.
Okay, I will think about it. And then I misunderstood something, but I guess
Yes.
the error is on my side.
Thank you.
Okay.
Thank you for a very nice talk.
Thank you.
My question is about the relation between the Dedekind reals and the ordinary Cauchy reals. And you could also formalize this with deterministic or single-valued Cauchy sequences. Have you also any results about saying like every Cauchy real is also any Dedekind real is Cauchy real is equivalent to some kind of non-constructive principle?
Yes, that's a good question. Actually, we are working on that question. And we can show that every single value Cauchy real, and the ordinary Cauchy real, defines a left Dedekind cut, obviously. But the other way is more problematic, and we haven't established a very strong resolved here, but we are working on that problem. Yes, that was the natural question that arises to this system. Thank you. Thank you for your question.
Any other questions or comments?
Could you show me the previous slide, last slide? So can you show such a, I mean, analytic version of logical principle like analytic WLPO or analytic disjunctive Markov is not provable in HAS 00 plus D?
Actually, for proving this equivalence,
Yeah.
we first showed that the decomposability of R implies sequential WLPO.
Yeah, but my question is, if everything is provable in the system, then this is, I mean, this theorem becomes nonsense, right? So I wonder, how can you show they are independent from your base theory?
Yes. One answer to your question is that we showed that the decomposability of R implies a sequential version of WLPO.
Uh-huh.
Sequential WLPO.
Okay.
Which we noted by this notation, for example.
Okay.
It says that every binary sequence alpha, for every binary sequence alpha, either all terms are 0 or not.
Mhm.
And sequential version of WLPO is not provable constructively, and therefore in this system we cannot prove that either. And since the decomposability of R implies sequential WLPO, therefore the decomposability of R must not imply in this system.
So, for example, if you add choice to your base theory, then everything is provable. Is it correct or not?
If we add choice, then
Extensionality.
I don't think so, because even with the axiom of countable choice, the sequential version of WLPO is not provable.
Okay.
Therefore, it's still not a trivial.
Okay.
Sorry, but what would choice mean? Because you don't have functions here, isn't it?
Yes. So, yeah, of course, we have to formalize choice
Yeah.
in
Yeah.
that context. Yeah.
Exactly.
Okay, thank you.
Thank you.
Any other questions or comments? Okay, maybe we should go to the next block. So let's thank the speaker again.